So now do we need to look at some things dealing with structures and what we figured out from Lewis structures and where we kind of go from here. So if I look at Lewis structures of H2, F2, and HF, what I see is they all look identical to one another. They all show a single bond, nothing really particularly different about their Lewis structures. But what I see when I look at the actual molecules are some very different things. I notice there's a great big difference in their bond lengths. Okay. F2 is almost twice as long as H2. I also see that their bond energies are very different from one another. So Lewis structures alone don't tell us the full story. While they're great and give us lots of information, sometimes we have to go on to a more advanced or complicated theory to truly understand what's going on within a molecule. So we're going to look at two different models. One is called valence bond theory, the other is called molecular orbital theory. And we'll look at valence bond first. It does a better explanation of bonding than Lewis structures are, and it's a relatively simple model compared to MO theory. However, when that doesn't work, and there are some things for which that doesn't fully explain the behavior and properties of a molecule, we have to go to MO theory or molecular orbital theory. It is more complicated, but it's even better than looking at valence bond theory. However, it does get quite complicated quite quickly, and so we'll actually only look at it for molecules known as homonuclear diatomic. So they have the same nuclei, and they only have two atoms. So things like F2, H2, O2, N2. So very simple molecules. So we've talked about covalent bond being the sharing of electrons between two atoms. And so we're going to look at our simplest covalent bond we have, which is H2 in hydrogen. And so what we've got is a single bond formed from each hydrogen atom sharing each of its electron with the other hydrogen. And we can kind of think of this as the spheres. The electrons are in those 1s orbitals. Those spheres coming together and overlapping with one another in order to share those electrons. So we get the overlap of 1s orbitals to form that bond. But now when we look at F2 or HF, what we see is we're no longer getting the overlap between the 1s orbitals. We're getting different orbitals overlap to form that bond. So when I look at F2, for example, we're getting the overlap of the 2p orbitals because that's where that vacancy is, and that's where fluorine needs to share that electron in order to form that bond. Same thing with HF. We have the 1s orbital of hydrogen with the 2p orbital of fluorine, and we're going to get that overlap happening between those two atoms as those orbitals overlap with one another because they're sharing those electrons. And so when we look at the differences in H2, F2, and HF, what we see is they can be explained by different orbitals overlapping. So H2 is the 1s orbitals overlapping, F2 is the 2p orbitals overlapping, and HF is one of each. And so not surprisingly, we see that the values for bond length and bond energy for the HF molecule fall somewhere between the H2 and the F2 values. So a question here, what orbital on chlorine overlaps to form the bond between H and Cl? So the bond here is similar to what we saw in HF. Okay, and so we know that empty electron is in a p orbital, so we can actually eliminate some of these options because they don't involve a p orbital. When I look at chlorine, what I see is that its valence shell is the n equals 3 level, and that empty spot is in the 3p orbital. Okay, and so that's where we're going to get the overlap forming to form that HCl bond.